Yeah, welcome. The topic we'll be discussing in this lecture is kernel data structures. So we'll be discussing few important data structures that were used by kernel. So basically the basic data structures are arrays and lists. Okay. So as we already discussed, memory is represented in terms of arrays. It is an array of bytes, okay, where each location represents a byte, okay. And if you want to store something more than a byte, okay, then you have to use more than one locations. So this is how memory is organized. So you can say that memory is organized in terms of array of byte. So it is implemented by using the data structure array, okay. So memory is implemented by using the data structure arrays, okay. But so use when you are using array, you can access any location directly. You can access first location or any location in between, or any location you can access directly when you are using the data structure array. But the problem with the array is whatever you are storing in the array, you should know the size in advance. How much byte it is, whether it is 1 byte, 2 byte, 3 bytes, you should know. Then only you can allocate in the appropriate location. Okay. So what if the size if you have a data which is variable in size? Okay, uh, that is the data may grow in size or it may shrink in size. In that case, what should we do? So we have another data structure called as list. So list is also a sequential data structure like array. Array is also a sequential data structure. So list is also a sequential data structure. That is, it contains sequence of elements. Array also contains sequence of elements. The, the main difference between list and an array is, in an array you can access any item directly. If you want to access first item, you access first item. If you want to access kth item, you access kth item. But that is not the case in list. If you want to access kth item, then you should access all the k minus you should access all the k minus 1 item, and then only you can access the kth item. Okay, you cannot directly go and access the kth item. Okay, that is the main difference between array and list. But there are certain circumstances at which list will be much useful, because in a list you can store data items which grows and shrink in size, okay. And also you can maintain the relative position of the neighboring data items. Say that I say that I want to delete one item from the list, but after deleting that also, the neighbor should not be disturbed. That is this and this should now become the neighbors. Okay? So such sequences can be maintained by using list. Okay, so and and not only that, and as we discussed, the 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 size of the list can each the size of the each element of a list can grow and shrink. Okay, each data items in the list can either increase or decrease in size. So whereas which is not possible in case of array. So in such cases we go for list. So basically there are three types of list. These are single linked list, double linked list and circular linked list. Okay, so what is a single linked list? So this is how a single linked list looks like. Okay, we call every element as a node. So basically single linked list contains a collection of nodes, and each node contains a data part and a pointer. So this is the data and here is a pointer. The pointer will point to the next data, or it will point to the next node. So again, the next node, it will have a data part and it will have a pointer. Okay, and this will point to the and this will point to the next node. Okay, this goes on. So there is no limit for the size of the linked list. It can grow up to any size. Okay, finally, so each one is a node. This is a node, this is a node. So everything is a node. Finally, if there is no other nothing to point. So if this is the last node of the linked list, then this will have a null pointer. It means it is not pointing to anywhere. Okay. So why we use list in the sense, uh, inserting data or deleting data becomes very easy and convenient with list rather than in arrays. Okay, say for example, now if I want to delete this item, so what will happen in the sense, just what we will do in the sense, we will make this nodes pointer to point here, that's all. So once you do that, it has only one pointer. So if it is pointing here, then it means it is no more pointing here, so it means it is already removed. Okay, similarly, if you want to insert something, say this is not, assume this is not deleted. Okay, I'll remove that. Say if you want to uh, insert something, then I want to insert a new node. Then what we will do in the sense, you create a new node. Okay, and keep it here. So I want to insert a new node between the node 2 and node 3. So I want a new node between node 2 and node 3. So this is node 1, this is node 2, and this is node 3. So here I want a new node. So just you make the pointer of the node 2 to point to this particular node, and you make the pointer of the new node to point to the node which is previously pointed by node 2. Okay, so now a new node is getting inserted. So this type of operations are possible uh, or are convenient with linked list rather than with array. So this is the reason why we go for linked list. Okay, so this is about single linked list. In case of double linked list, what we have in the sense, there will be two pointers. There is not just one pointer, there will be two pointers. That is, every node will have a pointer, a front pointer, and also a back pointer. Okay, so here the node will look in a double linked list. The node will be something like this. Okay, so let me draw. So each node will have two pointers. Okay, there will be a front pointer and there will be a rear pointer, and in between there will be data. Okay, if this is the first node, then the front pointer, there is nothing, there is no node before this, so this will be null pointer, so this will be null. Okay, and if there is a new node, there is another node here, then that node will be pointed by this particular back pointer. Okay, there will be a pointer in the front and also there will be a pointer in the back. So this pointer will be pointing to this node. Similarly, here there is a pointer in the beginning of that node that will point to the previous node. Okay, now this pointer will point to the next node. Okay, so this is the node. Fine. Okay, so here there is a data part. Sorry, here it is a pointer. Okay, here we have data, and this is the front pointer and this is the back pointer. So this front pointer will point to the previous node. Similarly, the next pointer of this node will point to the next node. Okay, will point to the next node, and here also we have front pointer and back pointer. This is the data part. Okay, so this pointer is pointing here, and this pointer will point to the previous node. Okay, so this type of linked list is called as double linked list, and if this is the last node, then this will be null. Okay, So the next pointer of the last node will be null. Similarly, the previous pointer of the first node will be null. Okay, in all other cases, the next pointer will point to the next node and the previous pointer will point to the previous node. So why we use double linked list? Because using double linked list, the accessing is more convenient because now you have double pointers. So you can either go this way or this way. So you have more accessing paths. Okay. So that is the advantage of double linked list. And similarly, the next type is called as circular linked list. So either single linked list or double linked list can be of circular linked list. In circular linked list, what happens in the sense, the last node will point to the first node. That's it. So here this is the last node and this node may point to the first node. So this may happen in single linked list also. If the last node is connected to the first node, then it is called as a single circular linked list. For a double linked list, if the last node is connected to the first node, and if the first node is also connected to the last node, then it is called as circular linked list, doubly circular linked list. Okay. So this is about the data structure list. So especially for dealing with memory, mainly linked list is used. So the operating system uses linked list for accessing memory locations in an effective way. Okay. So the next data structure will be binary search tree. But before going to binary search tree, we will discuss another two data structures. These are stacks and queues. Okay. You might have heard these words. One is stack and the other one is queue. So what is a stack and what is a queue? Okay. So stacks are also called as lost in first out. The data structure stack is also called as lost in first out. Okay. So whatever the data item that you insert lost, that will be coming out first. Okay. And one end of the stack will be always closed and the other end will be opened. Okay. So you can see something, you can visualize stack as something like this. So here items can be added to the stack by using push operation. Okay. So stack supports two operations. One is called as push and the other one is called as pop. So if you want to add anything to the stack, then you use something called as push. If you want to remove something from the stack, then we use something called as pop. Okay. So when you push anything to the stack, it will come here. So say for example, I push item 1, then item 1 will come here. Okay. So then if I push item 2, then item 2 will come here. Okay. If I push item 3, then item 3 will come here. Okay. And when you pop anything from the stack, the whatever the top, that will be popped out. So if I perform pop, I3 will come out. Okay. I3 will come out. Now I3 is not the top, it is already popped. So now I2 is the top. Again, if I perform pop, I2 will come out. Okay. So now I2 is not the top of the stack, I1 is the top. Again, if I pop, I1 will come out. Okay. So now the stack is empty. Now I cannot perform any more pop operation. If I perform pop, it will fail. Now you can only perform push operation. So you can perform push operation as long as the stack is not full. Once the stack is full, it will not allow push operation. So stacks are used extensively in computer science. Mainly stacks are used by operating system for dealing with function calls. Okay. So whenever the operating system want to say assume the operating system is executing a program, okay, or a function, let us call it as function 1. Okay. And at one point of time, this function is calling another function. So it is calling another function, function 2. Now what happens in the sense, the control should be transferred to the next function, which is called as function 2. So, but before transferring the control, what happens in the sense, it has to, it will, whatever the current status of the F1, whatever the current status of the F1, in terms of what are its register value, what are its other parameters, everything it will pop into stack. F1, all parameters related to F1 will be popped into stack. Then it will go and execute the function F2. Okay. After finishing execution, it will come back. After coming back, it will pop from the stack the F1 contents so that it can resume the execution, because all the parameters it has stored in stack, now it will get back. So this is one example of stack. Like that, stacks are used at several places. Okay. Similarly, there is another data. So as the last input data is coming out first, it is called as LIFO, last in first out. Similarly, we have another data structure which is called as queue. Okay, so the data structure queue is also used to a larger extent in operating system. So what queue does in the sense, so queue follows something called as FIFO. FIFO stands for first in first out. It is the data that is inserted first, it will come out first. Okay, the data that is inserted first, it will come out first. So it is something like a normal queue, you can assume. The queue that is in a ticket counter. So whoever the first person in the queue, he will be the first one to come out. Okay. So in a queue, what happens in the sense, the both ends of the queue are open. Whereas in a stack, one end is closed, the top end alone is open. And deletion takes place through the front end. So this is called as front end, and insertion takes place through the rear end. If any new entity should be added into the queue, that will be inserted through the rear end. Okay. So this is how a normal queue works. I think you can relate it. So here, whoever the person who enters the queue first, he will be the one to come out first. Okay. So the in computers where we use in the queue, in the sense, there are several places. Say for example, one of the most relevant example will be print queue. Say you have a printer. Okay. Say the jobs are submitted to the printer. Maybe multiple jobs were submitted to the printer. Say 3 jobs were submitted to the printer. Then what will happen in the sense, the printer will maintain a queue, and all these jobs will be stored in the queue, and one by one the printer will execute it. Okay. So job 1 will be stored first in the queue. Okay, this will be the first to enter the queue. Okay, then there will be job 2, then there will be job 3, and then there will be then there will be job 2 and job 3. So what the printer will do in the sense, first it will take job 1. First it will take job 1 and it will execute it. Okay, this is 1. Okay, once it is done, it will be removed. Okay, so because the queue entries are removed from the front, then it will take job 2, it will execute, that is, it will print it, then it will take job 3. Okay, like that we have process queue also. Okay, whatever the order in which the processor accesses the processes, so that is also maintained as a queue. Okay, so this is one of the important data structure which is commonly used in operating system. Now let us try to understand what is a binary tree or a binary search tree. So before that, let us understand what is a tree. So a tree is something of parent-child relationship. A tree is a data structure which maintains parent-child relationship. So there will be a parent node. So these are called as nodes. This is a node, this is a node, all these are nodes. There will be a parent node, and a node can have any number of childs. Okay, so that is a general tree. A node can have any number of childs. But first we will discuss what is a binary tree, and then we will discuss what is a binary search tree. In a binary tree, a node can have only maximum 2 childs. A node can have only maximum of 2 childs. Okay, so one will be the left child, the other will be the right child. So such a tree is called as a binary tree. So this is an example of binary tree. Here you can see every node has two childs. So this is an example of a binary tree. A node can have at most two childs, not more than that. What is a binary search tree? A binary search tree is one. A binary search tree is a binary tree. First, it should be a binary tree. That is, uh, the node cannot have more than two childs, and then the left child will be always lesser than the root node. Here, this is the root node. Okay, the left child will be always lesser than the parent node. Okay, so 12 is lesser than 17, and the right child will be always greater than the parent node. 35 is greater than 17. Similarly, if you see 6 is lesser than 12 and 14 is lesser than 14 is greater than 12. Similarly, 32 is lesser than 35 and 40 is greater than 35. If this sequence is ensured, that is, if the left node is lesser than the parent node and if the right node is greater than the parent node, then such a tree is called as a binary search tree. Okay? So why we maintain this tree, all these things means it is a one form of data structure. All these things the operating system does only to access data in a faster rate. Okay. So if say for example, if operating system want to access some data, then it will follow that order. In case of a binary search tree, what it will do in the sense, say if you want to, if the operating system want to access 14, the number 14 in this tree, then it will check first 14 with the root node. What is the value of the root node? 17. Is what it want to check 14? Is it greater than the root node or less than the root node? It is less, so it will come to the left side. Okay, then it will take this value 12. It will compare with 14. Is the 14 is greater than 12 or less than 12? It is greater, so it will go here. And now it finds the data, it will fetch. Okay, like that the operating system accesses the data. To access data in a faster or in a quicker way, it uses this. Okay, but still the worst case performance of a binary search tree is order of n. That is that is that is it may have to go through n levels. So these are level. This is level 1 and this is level 2. If these are levels, okay, it may go up to n levels for a particular data in worst case scenario. Okay, so for example, here n represents number of values. So sometimes it may, here this tree contains 7 values. Sometimes it may need to go up to 7 levels also. Okay, there is another advanced concept called as balanced binary search tree. So balanced tree, it means there are some mechanisms to balance a tree that will be probably will be discussing in design and analysis of algorithm course. So there are some mechanism for balancing a tree. So if it is a balanced binary search tree, then uh, then the performance will increase by order of log n. That is, it will have maximum only log n levels. It will not have n levels. Okay. So as of now, you just understand that the binary search tree, a balanced binary search tree will perform better than a binary search tree. Okay. Here n represents level. Log n will be surely lesser than n. So it can access the data at a very faster rate because it need not go up to n levels. It can get it in log n levels. So that's it about binary search tree. Okay, I think we will stop here. So there is another data structure which is called as there is another data structure which is called as hash function. We will see it in the next video. Okay, thank you.